A good way to pose questions, one way to pose questions is to look at the faults you've had in the past and debugged, and to come up with your own ad hoc list of questions. I know that it's useful to go and check these TCP statistics. I'd run netstat -s and go and read these things because it means X. I know it's useful to go and check these particular metrics out of the kernel. The problems with coming up with an ad hoc list of, well, on the plus side, it works because you've had those issues before. Now you've added them to your metric system and you are indeed solving things. The problem is the unknown unknowns, where you just aren't aware that you should be, like the issue I worked on with the CFS arc, where the CFS arc was shrinking in size and making it look like we had a disk I/O issue. We weren't looking at that statistic, we weren't monitoring it. It's coming up with a list of metrics to monitor based on past experience is bounded by that past experience. But there's a different way that we can use to come up with these metrics. That's great, and that's a really useful exercise, is to talk about our past experiences and figure out what metrics to create. But the other one is to come up with methodologies that pose the questions. So I've documented these on my blog in talks before, in my latest book. And to briefly explain what they are, work-like characterization has been around for a long time. Like, you can read about it in, anyone know Raj Jain's Art of Computer Performance Analysis? It's a great book. That's 1991. I don't know what the origin of this as a methodology is, but it's been around for a long time. With work-like characterization, what I want to do is take a system and look at the input applied. Now, as a methodology, it's useful because we don't want to get wrapped up in resulting performance. We want to look at this is, for example, disk workload characterization, what was sent to the disks, and that's it. Do you think it's possible to diagnose a performance problem just on those columns? Customer says, my disk I/O latency seems a bit bad, and you look at those 4 columns. Could you diagnose it? Yeah, it could be like, well, you're doing 4,000 reads a second, and the system doesn't have that many disks. So before I even look at the rest of it, I didn't even know the disks could handle that many reads a second. Maybe it's a problem of load. I can go and check the other ones, but that's really useful information to know to start with. For network throughput, you may say my web server is a little bit slow, and you find out that it's on Hacker News right now, or Slashdot. And you're not looking at any resulting performance. It is just the load applied to it. Could you diagnose a performance issue with just knowing that you are currently #1 on Hacker News? Like, absolutely, like that's really useful. And that's why it's separated out as its own methodology. I'll tell you one really good GUI for doing workload analysis, and that is Google Analytics. So you can look at, I can bring it up from my blog. Google Analytics, when you're using it for a website, shows the load that's applied, and you can do various breakdowns. Who's applying the load, what different targets were they applying it to, and so on. So why am I listing it as a methodology? It's because it poses questions for us to answer. It is who, why, what, and how. Who is what users are applying the load. So imagine you're designing metrics for your system that provides a service to the internet. So it's a mail server or something. Who means you want the metric to answer who is accessing the mail server. Why? Because you might find it's being denial of service attacked from a group of hackers or crackers. Really useful. Who? Why are they accessing it? I often do this for disk I/O analysis, and that's where I'm understanding why did we end up causing this disk I/O? Is it because it was a cache miss? Is the file system doing something unusual with the inflation or deflation? coming up with metrics to understand why something was caused, the type of load. What the targets of the load were, so you can imagine what metrics. So for disk I/O, the what metrics would be reads per second, writes per second, kilobytes read per second, kilobytes write per second. If it's websites, web traffic, it would be the targets. If it's an AP, like the APIs that you're calling. So what are you actually requesting of the system? In fact, for disk I/O, you're missing one. We're often failing to track SCSI commands. And so I've debugged a bunch of disk performance issues which are caused by the SCSI cache flush command. And that's not part of IOSTAT. And so you can't see that you've got that latency. It's because we just haven't added it. It's a missing metric. We need to add an extra column to IOSTAT that says these are the non-data transfer commands, SCSI commands that are being sent to the disk. Because, hey, they exist, and they can cause latency, and they can... So, what? So everything that's actually being, the targets that's being sent. And then how, I would say, is how is it changing over time? That's also an important metric for workload characterization. Everyone building a monitoring system is already good at this, where you're archiving the statistics, and you can see that there is a daily pattern, there is a weekly pattern, and so on. So that's it. Let's workload characterization. The idea of me describing it like this is not to force you to obey this particular model, but it's to give you ideas for metrics. That's it. And if it works, it works, and if it doesn't, it doesn't. It's no sweat. So if you go through the workload characterization, you're writing your own application component. Try it. Who, why, what, and how. See what metrics can answer those questions, and implement them. And if like, why doesn't make sense for this thing, it doesn't matter. These methodologies are about posing the questions we'd like answered before reaching for the solutions. Because quite often what we do currently is we look at the metrics that the application and the OS provides, and then we try and make sense of them, instead of doing it the other way around. That's fine, because you will solve a bunch of problems that way. But I'm proposing these methodologies because there is a different way to get to the metrics that allows us to design them. Latency analysis, drill down analysis. To summarize that methodology, that's when I have a stack of components, like my disk I/O stack, and I would like to know detailed latency metrics at each layer of the stack so that I can perform drill down analysis. So if I have my stack and I see 1 second, I have metrics 99th percentile. I see 1 second 99th percentile at VFS. Down at ext4, I see 1 second 99th percentile. Down at the block device interface, I see 1 second 99th percentile. Down at the disk driver, I see nothing. I then know it's a problem with the block device interface. I can go and look at this queuing, its I/O scheduling. So with latency analysis and drill down analysis, what metrics can we come up with that give us a reasonable idea of latency? And I would say that would include things like the mean, the standard deviation, the median, the percentiles, the min and max, like as Theo said, the 7 metrics. But it would also ideally include a full histogram in addition. Come up with that list, and now do it at the different components of your stack. Now for drill down analysis, that's where I will move down the components to try and see when the latency vanishes. And when the latency vanishes, I've isolated where I should start looking. If you have a distributed system, which we can talk more about in a bit, you can do something similar where I can correlate these latency metrics between components. Event tracing is a methodology. Event tracing is where, instead of trying to come up with statistics that, trying to roll up and have summary statistics, you log all the events. And I know some people are doing this, is gathering logs, especially if it's application access logs. But you can also do this for anything. So this is why it's a methodology. When you're thinking about instrumenting my system, think about, should I just have an event log? It depends on the frequency and the overhead for that. So for example, you couldn't do an event log for CPU instructions or memory accesses or maybe not even VFS level I/O. With VFS level I/O, you're going to the file system cache, you can do millions of events per second. It's like trying to log every syscall. But for disk I/O, once things have been returned out of the cache and buffered, that may be infrequent enough that you can start to log every event. And certainly for database queries and application requests and so on. So there's the methodology. If you have the log, you can then go through the log and read all the components to understand exactly what the makeup of that operation. And as part of the event tracing log, you might include workload characterization details. So who, why, what, and how. And so the log may alone explain an issue, but you might then build tools that repurpose that log to answer the other questions. There's another type of log which is useful to bring up for event tracing, and that is the MySQL slow query log. And so instead of tracing every event, you may put a threshold and say 100 milliseconds is bad. Only log events more than 100 milliseconds so that I don't have a giant log problem. That's okay. I found an issue with choosing a threshold like that is that sometimes the performance problem or the latency is caused by the lead up. And the system acts as like a queuing system where you may apply a burst of load. Most of that returns very quickly, but then as it all entirely gets queued and then it operates through the queue. And so the service times start getting higher and higher and higher and higher, and you eventually trip your slow query log or whatever it is, your threshold. And if you're looking at that log and you're trying to understand, I've just got this burst of 100 millisecond API calls, how did I get there? You've lost the lead up, and so you've lost the activity. And so a slow query log or a slow API log or whatever, it's better than nothing, but sometimes I need to turn on the full log so that I can understand the lead up. CPU profiling is another methodology, and this can be built into monitoring solutions. It is a simple way to really understand what code is on the table, or what's actually being active by profiling what an application's doing. And just to give a picture example of this, actually got my slide deck. Just give you an example of it. One example. I'll be doing this on Thursday. I've got a talk on flame graphs. Flame graphs are visualization of CPU profiles, and what it does is it will take stack samples of the target, and then instead of giving you a time series, this shows it sorts alphabetically, and so it shows you the entire population. And it does that so that it can merge together stack frames. So this is stack depth. And so I can take one of these and very quickly, I can't mouse over it because that's my slide deck. Let me show you the real thing. It's in, ones that I'm working on. That's a kernel. These are all different system calls, and I can see the path that they're taking. I have a less dramatic one. Oh yeah, this is a customer issue I was working on last week. It doesn't, fortunately, there's no details accidentally revealed, but it's where I'm profiling Sphinx, which I don't know a whole lot about. I'm not a Sphinx internals expert at all, and so the customer says they have a performance problem with Sphinx. By CPU profiling, what it gives me is I can navigate through these paths, and now I know, okay, so we're spending a lot of time in get docs chunk, 97% of our samples, and we're spending 40% here and 55% over there. And I can actually go through all the code paths and figure out why we are using CPUs. That's neat, that kind of sounds like this doesn't sound like a methodology. This just sounds like a tool for debugging CPU issues. We are using it as a methodology often because this tells you what code is on the table and shows what's currently being active for the application. I actually had an earlier Sphinx flame graph, so I was able to do a comparison over time and see what changed. So now that there's an issue, what parts of the code are now active that weren't active and vice versa, so that I can do that difference. Now, I know for monitoring, we're doing a lot of comparisons of line graphs, hopefully heat maps, where it's really important to see differences over time. And so now we're doing the same thing with flame graphs, where this is what the application was doing. This is where it was spending its CPU time. Now compare that from the past to today. So it has been hugely useful. That example, this is an example where we were doing a disk benchmark, or a customer was, and they were getting throttled. And we just forgot about the throttle. And just turning on profiling so that you can see what code was on the table. Like I looked at this and I'm like, oh, I'm an idiot, the throttle's turned on. And they're trying to benchmark the disks. So, very, very useful. But we are starting to use that as its own methodology to see how things change over time, just to understand, just like you currently use, I know it's very strange, just like you currently use a set of metrics to characterize what a host or an application is doing, this is using stack samples to characterize what the application is doing. Now, what's thinking? Cache tuning is another methodology where, with cache tuning, we're interested in tuning the workload for the cache and the cache for the workload, where we may be matching record sizes so that we don't pollute the cache, and making sure we don't pollute the cache, whatever the cache is, with not so useful data. And so caches can be anything. It could be application cache, file system cache, CPU caches. What metrics would aid cache tuning? Well, with cache tuning, the metrics that would aid it would include the hit and miss rates, the hit and miss ratios, especially the miss rates, because that's the measure of pain when you actually miss out of the cache. And so just something to include as part of methodologies is metrics for the caches. The use method. Now this is where, this was published this year it was published in ACMQ and CACM, and it is very simple. If I bring up my summary of it. So, by the way, when I'm listing these methodologies, this isn't all the methodologies you can do. This is just 7 that I happen to pick as these are very, very useful ones. But each of these methodologies poses questions, and those questions can be answered by metrics. And there's no one methodology that solves all issues. Think of it as like a toolbox of methodologies, where each of these methodologies solves a different set. The use method is aimed at system bottlenecks and errors for resources. It can be summarized in one sentence. For every resource, check utilization, saturation, and errors. Resource is all the physical server functional components, including buses. It can also be software components. So you can apply this to a software system as well.
Sorry, how easy is it to check the bus saturation on any operating system?
Hard.
Yeah, like just checking. I straight away thought, I can't do that.
Yes. How easy is it to check bus saturation? Hard. And I worked with some of the engineers who worked on the CPU performance counter support in the kernel, and one of the reasons it's hard and we don't have good tooling for it is that customers aren't asking for it. And I've debugged issues. I've had many issues of bus saturation, because processors are getting faster, but buses are not at the same rate. Memory is not at the same rate, the memory access latency. And so understanding CPU interconnect utilization, memory bus utilization, these things are becoming more and more and more and more important. But these aren't typical parts of the metrics people go and look for. So for this methodology, like the other methodologies, I'm not starting at what's easy and what's hard. It is hard. It's hard to do this. I'm starting at the questions we actually want answered to satisfy this methodology. And then we go and then we see if the metrics exist. And if they don't exist or they're hard, we try and improve it and make them better. So yes, buses are hard. Utilization is the average time a resource is busy. Saturation is the degree a resource has extra work, which it can't service, often queued. And errors is the count of error events. When I say every resource, I mean a functional diagram like, if you can find something like this, it's great. This happens to be an old server functional diagram where I can go through each of these components and ask is there utilization, saturation, and errors for each component. What you want to do is you only want to hit up the ones on the data path. So your server may have, most things are on the data path, but your server may have, functional diagram may include an audio card or a speaker or something like that. It's not part of your data path. Work through your data path, what functional components exist, and then ask utilization, saturation, and errors. How many physical components are there going to be in a system? Not that many, like 10 different types, maybe. Now, I'm only asking 3 metrics for them, utilization, saturation, and errors. So you end up with maybe 30 metrics. And that's the use method. The use method solves a lot of problems because it focuses on those with bottlenecks and errors. To see how it's implemented, I've been posting these for different operating systems, version of the use method, and I iterate over the hardware components and then those 3 metric types: utilization, saturation, and errors. CPU utilization, how do I measure that? Well, there's tons of ways. Look, I've even left dstate in there. There's tons of ways I can do CPU utilization. This is a really, really, really solved problem. For the use method, by the way, you do want the discrete components. Bless you. I don't want average CPU utilization, I want it per device. CPU saturation, tons of ways to do that as well. I can even run perf shed latency to look at the average delay per schedule, because the Linux kernel has the scheduler tracing framework, scheduler latency. I can also run dynamic tracing if you want to use system tap or dtrace and run the risk of something bad happening until they're fixed. CPU errors. That gets a bit harder. So perf, which is Linux perf events, if processor-specific error events are available. CPUs have various error events. They include things like CPUs can go into thermal states where they will wind down because they think they're cooking themselves. How many people are monitoring that? Yes, fantastic. CPU thermal. Well, are you monitoring it because of the stall cycles, the temperature stall cycles, or are you monitoring it from the temperature probes?
We're monitoring it via syslog. So it goes to the central log server where it throttles it.
Yeah, we actually have gotten some kernel log events when a power supply was working on failing because it was like unable to deliver sufficient power to fully ramp up the CPU.
Okay, I wonder if that's speed step or if that's actually, because there's 3 different modes of thermal throttling. Anyway, great, fantastic. It doesn't matter if it's how you're doing it. If you're doing it, it's great.
One of the things we're useful to do is to turn off machine check exceptions causing kernel links and movements, and have the machine live around long enough to report error. There's a lot of errors that do get stored by it that we do not get these, right? So yes, the reboot is generally not the right answer in this server run.
Right.
One of the broken machines hanging around wanting to be diagnosed rather than reboot.
Don't you get a panic and those sort of reports?
Sometimes.
Like the MC doesn't hit a particularly bad part of the kernel, you just see the MC come through and it'll keep on running.
Or sometimes
You'll just see, you know, there's a constant log output, which your terminal server might look greater.
Yeah, yeah, having undiagnosed kernel errors is very bad, obviously. The place I work has the philosophy that crash dumps by default is mandatory because they're considered a black box. And so every panic, we get that black box, we debug it, we fix it. I've done crash dumps on Linux. It's a bit harder. At the moment, you've got kdumps and the capture kernel and all that stuff. Who does crash dumps on Linux right now? Good, great. I actually have more hands than I normally get. Great. Yeah, really important if you can set it up so that you can, as you said, so you don't have reboots that go undiagnosed. You want to diagnose it, however you do it. So, CPU errors. As another CPU error I was benchmarking a system once and my throughput went down by 20%, and I couldn't explain why. And I was stupidly didn't follow the use method for about an hour as I was looking at all sorts of different things. And I finally followed the use method and a CPU had failed. And this is on the Solaris kernel. Solaris has fault management architecture. It will predictively look at ECC errors and then offline a CPU before it causes a panic. And I just didn't check the log for an hour. And then I checked the log and it's, I'm an idiot. I'm down one CPU. So CPU errors can cause performance issues. But there are a bunch of, apart from thermal, there are a bunch of error states that you can only get out of the performance counters, which gets hard to monitor. Memory utilization, then I'm talking about memory capacity, I'm talking about how much memory there is. Once you get saturated, it depends on what the operating system does with it, whether you're going to get the, I need to mention the killer in there, whether you're going to get the killer on Linux, or whether you're going to be doing paging and swapping. Network interfaces, so utilization, saturation errors, same thing. We want to answer those three for all of those physical network interfaces. That should be straightforward. Storage device I/O. That's where you can get it out of the kernel. If you go sys devices, there's an I/O CNT, there's smart CTL. Someone mentioned dmessage, shows up in dmessage sometimes, great. So do want that as part of what I'm monitoring. Storage capacity, straightforward, TF minus H. Storage controller utilization, saturation, and errors. So you can definitely have issues of storage controllers where they're maxed out. If you have lots and lots of disks, storage controllers plugged into a PCI bus or whatever, it has a max, actually the bus is separate. The controller itself may be a bottleneck. It may have a maximum number of IOPS it can possibly do. And so being aware that this can be a bottleneck, it's actually kind of hard to do in Linux. Because in Linux, in other operating systems, IOStat has a cap C for per controller statistics. Linux does not. So in Linux, you look at your device list and then you mentally sum them so that you can figure out, oh, this is how many IOPS are actually going through my controller. I know what the controller limit is. I can now figure out utilization. How do you know a controller limit for your storage controller? So two ways. Look at the vendor documentation or do micro benchmarking. And just ramp the load up until you hit a ceiling and try to make the load as fast as possible. Network controller, same thing. Network controllers can have limits. That might actually be your system bottleneck. Also, kind of difficult to do in Linux right now. Then we get into the buses, which I already said was hard. That's Linux performance events, CPC, and CPU interconnect utilization, saturation, and errors, memory interconnect, I/O interconnect. I've done this before. Generally, you get the vendor manuals like the Intel or AMD or whatever, and you spend a week reading the appendix, which goes through the performance counters, and then you can roll the tools to measure them. There are some IDEs that make it easy, like Intel has vTune, there's the Oracle Studio, but a lot more work can be done to make this easy for us. It's just painfully hard right now. What would I like to see? I'd like to see a bus top, which showed me the buses and then their utilization, saturation, and errors to make it easy. Which is why I feel a little bit of disdain when I see yet another top has been created for Linux. it's like, which just does the same CPU columns and what have you. This is the unsolved stuff. It's really hard to do. That would be fun to.
Are these metrics actually exposed in some kernels, or were they tracked into the chipsets that they run on, like chipset drivers, and pull this stuff out?
A lot of kernels can access it, but how many kernels will, by default, pay attention to CPC? I have only heard of one, and that was the Google CPI squared project, where they're looking at the CPI metrics to try and figure out, does this sound familiar to any Google? I'm sure there's lots of projects you guys do. CPI squared was where they're monitoring the cycles per instruction to try and figure out if there is a bad application that's monopolizing the memory bus, and then it can change the priority of that application. And that is the only time I've heard of this being just monitored 24/7, being used, which is really cool. I think it's great.
And do you know what they were doing exactly? They were just instrumenting the scheduler to kind of checkpoint these counters.
They were able to figure out CPI as different applications were running. And so if one application starts to do, because the problem with CPU scheduling is, we're all in time-shared systems. We want to prioritize users. I want to give tenant A 10 milliseconds of CPU time and tenant B 10 milliseconds of CPU time because they're supposed to be even. What if tenant A, in their 10 milliseconds of CPU time, stomps all over the CPU hardware caches? Well, tenant B is now running slower. But you didn't account for that when you're time sharing. And so that's, as far as I understand, why Google was interested in exploring this. And when tenant A is running, measuring its, ideally you'd measure what effect did you have on the caches, but that's actually really hard. Using cycles per instruction is a generic way to do it, so that you have a rough idea of how much you've hurt a bus. And so that way they could then determine that actually, to be fair, this shouldn't be 50-50. Tenant A should run for 8 milliseconds and B should run for 12. That would be a more even distribution of CPU resources, because just of the way it uses the caches and the memory buses and so on.
Where, and they would say, well, there's a high number of, and from that we infer that it's stepping all over the cache.
Correct. So cycles per instruction, it's a great metric. As John said earlier, isn't all of this stuff hard? There's one thing that's actually not that hard, and that's cycles per instruction. Cycles per instruction, it means how many cycles did it take to complete processing this instruction, or to retire the instruction. The higher it is, the higher the latency is, the longer it took. And that usually means you stalled on cache misses, memory buses, interconnects, could be TLB misses, all of that stuff. So cycles per instruction, very rough way to find out if there is some bus, maybe it's bus pressure or memory pressure or something else, but if my CPI goes up, it's a rough indicator.
So whenever I've done this before, I did a really crude thing, which is just pin it to a single CPU and see does it get better or worse.
Yes, usually does get better because of cache affinity and.
Right, exactly. You might have this thing where you were running 10 threads on a CPU system or something like that, and also let's look around stuff and say, okay, run one thread, run another CPU and see what might see its occasionally, but okay, something was caching its, flashing its caches. Is there better than just pinning it to CPU?
Yeah, you can measure. So these events, and pinning things to CPUs is great. It's an experimental approach. For observation, on Linux you've got perf. You can use perf to, it's the hardware events, and you want to probe the. So I've got various hardware events here, like cache misses. I'm running this in VMware, so it's amazing that I have any at all because it's synthesizing it. But on a physical box, you'll have a lot more hardware events. I can say things like, for every 10,000 cache misses, give me an application stack backtrace. Okay. Now it's telling me what parts of my code are causing these stall cycles or memory bus usage and so on. I can then read the Intel manual and then split apart cache misses into all sorts of different types. So level 1, 2, and 3 cache misses and memory bus and resource bus and interconnects, whether it's local memory, whether it's remote memory. And so yes, you can dig down and get much more information about the problem, but one of the most useful high-level things is simply, why is my code causing memory stall cycles? Why is my code stepping on the cache? Because at Sun, over and over and over, we had these zero-copy projects. And the notion of a zero-copy project is when your application gets a buffer and an I/O request, and then it services it, how many copies do you make of that buffer to service it? Because each copy means you're doing memory work. And if you can design your application to operate on the buffer without doing any copies, you've reduced the memory load, and you've reduced the stall cycles, and you've improved cache affinity. But this is just an example of the sort of things that this can help lead to.
But doesn't that sort of presuppose that you're not like running in a Java VM or running Python or something like that, where you actually control the C-level calls in order to manage those resources? Because from an operations point of view, really all I can do is pin it to the CPU and stop it from crashing. Or does it respond to me?
Yeah, right.
You can let it vote against yourself in terms. I should really rewrite this.
Yeah, I really need to rewrite Java, but you know.
No, this isn't just problems of the JVM and the language virtual machine implementation. What I would do with Java is, and you can do this with dtrace at least, is I can profile cache misses and then show the Java stack trace and show the objects, methods, classes that caused cache misses. And then I can tell the program developer, my application developer, why are you allocating all these objects? Can they be smaller in size? Can you use fewer of them, et cetera, et cetera. So you're right, like fixing the JVM part, but fixing your code, much more within reach. So anyway, that was the use method. I also have some examples there for software resources like kernel mutexes, user mutexes, tasks, file descriptors. This doesn't solve all issues. This only solves a particular class subset of issues involving bottlenecks and errors. But what it does provide you is with a way to pose questions that you'd like answered. And it's only a finite number as well. Ideally, I would like to see use method wizards in all monitoring solutions. So when you build a monitoring solution, I click on the use method and it shows me this breakdown. If we start doing that, and I already know companies who are, I imagine for some time these are going to be blank because it's just too hard right now to measure all those interconnect utilizations. That's fine, totally fine. I like to know what I haven't measured, because if I have, in many cases it's fine. If I have that really urgent customer issue where the CEO is saying, Brendan, you absolutely have to fix this, it's really urgent for the company, that's when I'll say, all right, I already have a to-do list of things that I know I didn't measure because it's too hard. Now I can go and roll the hard tools to do it. So these methodologies, they may pose these questions that you can't answer of the system. That's useful because you're now aware that you can't answer it. And you've created a need, and over time, kernel engineers and application developers and people writing monitoring software can add those metrics.
Do you have success and failure metrics for the use of the use method itself?
Success and failure for the use of the use method. So far, it's pretty successful. Although people do panic when they see this stuff.
No, I seriously actually mean from within Joyhan, when you have approached. Is this like, this is Brendan's checklist, or do you have actually more systematic use of it within Joyhan?
At the moment, it's because I've created this for Linux and SmartOS. The support team are using it as checklists. Like one of the guys I work with, he has them all bookmarked. He goes to it all the time. We have added metrics on purpose into our monitoring software so that we can do some of these items like per device utilization more clearly. But the support, our support group likes to work through a method, and they have like a wiki page for this sort of thing. So that helps. I've also been running classes where I've taught this to other people as well, and it is a concise thing that's learnable and that people can follow, whether you're a beginner through to an expert. And so it has been pretty successful.
We're 10 minutes over lunch.
Yeah, we should break for lunch almost right now.
10 minutes ago.
10 minutes ago, thanks. So that was Methodologies. When we get back from lunch, what I'm going to do is have us work on coming up with some ideal metrics, and we will come up with a list of what we want to attack and break up into groups. Any questions before we break for lunch? Okay, thanks. Let's
I'd love to see some like perf.
have used perf in production, and perf also lets me experiment with creating new metrics. So we live in a world where it's not an academic exercise for us to get together in a room and say, what are the ideal metrics we'd like to measure? We can actually try it out. We can go use one of these dynamic tracing things, see how well it works. And then over time, it may be implemented permanently. I know for some sites, what they have is, because dtrace is so good at this, their main environment is Linux, and then they use some, whether it's a Lumos or FreeBSD nodes, which is basically their oscilloscope. And they try out metrics and try out analysis, and what they determine off those nodes then goes into the in their main Linux distribution. So, however, we should feel liberated that we can design new metrics and put them into practice. Then we had some good discussions. We talked about I/O, and Theo and I talked about different ways to expose and analyze metrics. I talked about methodologies and how these can pose questions that lead to metrics. And I was just updating this a little bit. So workload characterization, the sort of metrics that are suitable for workload characterization includes your IOPS, your throughput, user IDs, URL. It is take the workload and characterize it without looking at the resulting performance yet. Latency analysis, drill down analysis. That's where I want to have rich latency metrics for my distributed environment or at different layers of the stack. And you may come up with the 7 statistics: mean, min, max, standard deviation, MAD, etc. Plus a histogram, so that you can, when you need to, you can properly see the full distribution, whether it's multimodal, how the tail looks, and so on. And the use method, which is what I finished with, and the use method proposes 3 metrics: utilization, saturation, and errors for every component. It's really useful to think of the questions before you reach for the answers, because sometimes by starting with the tools and the metrics the OS, the applications, and the monitoring software gives you, you will have gaps in your observability. And it can be very, very easy to think that this monitoring software, surely everything must be visible. There's just so many graphs and so many lines and so many metrics. Surely everything I could need is already there. And often that's not the case. And so you need an exercise to figure out what's missing. That's actually really hard. It's easy if I told you to find things that are present. That's an easy exercise. Can you do this and can you do that? Finding things that are missing is harder. It's the lack of something. It's what methodologies can help get you to unearth.